I know I piqued your interest because this video is great. This is minimum absolute difference between elements with constraints. Problem number 2817. Okay, so let's go ahead and get right into this problem. So you're given a 0 indexed integer array nums and an integer x. Okay, so we are given in this situation x and nums. Now you're going to find the minimum absolute difference between elements in the array that are at least x indices apart. Okay? In other words, you're going to find two indices I and j such that the absolute of I minus j is greater than or equal to x, and the absolute nums I, nums j is minimized. So that's basically saying, if we have an array like 4, 3, 2, 4, for example, right? And x equals 2, well, in this case, right, you might say, well, the closest elements are like, 3 and 4 right here, right? These two elements are as close as possible in terms of their value, right? Because the absolute value of them subtracted from one another is 1. So that's the minimum value. Therefore, the answer is 1. Or I'm an idiot because there's even a better example, right? If they were adjacent, but the actual answer is here, right? Should I restart this video? No, I'm not going to. So here the answer is 0 because there's this 4 and this 4, right? So if nums of I is 4 and this nums of j is 4, you subtract them, you get 0. You get the minimum difference between elements in this array, right? Not the best example. Let's see if this example, this example, they're 1 away. It's so annoying. One thing that's always annoying about these kind of problems is sometimes they don't actually provide you with examples that are helpful, right? None of these examples are really that helpful because it doesn't show the nature of why this problem is a little more complicated than something you may be familiar with. And that is, let's imagine that instead this array looked as so. Just for the sake of trying to understand. Let's say it was 1, 2, 4, 4, and x was 2. Well, in this example, right, you would say, well, the closest two elements are still 4 and 4, right? Because that would minimize the difference between two elements, right? Because we're trying to find elements that are as close as possible to each other, right? If you're trying to find the minimum of, the absolute value of x minus y or whatever, another way of stating that is you're trying to find closest x and y's. Can't see my screen. So you're trying to find the closest x and y's, right? You're trying to find the x and the y, the values that are as close as possible to each other because that will minimize the difference, right? If you want to minimize the difference between things, then you put people together that are as close as possible to each other, right? If you want to minimize the difference between people's heights, then you put people of similar heights next to each other, right? So you're trying to find the thing that's closest to it, right? The thing that's most similar to it will result in the smallest difference between the two. Right? That's kind of the logical thinking of how I can restate this problem, right? And that will become apparent in a second, right? So the closest thing to 4 is another 4. So you might be inclined to say, oh, well, then therefore I can pick these two. And these two 4s together will result in the minimum difference. 4 minus 4 is 0. I'm good. But the constraint here is this x equals 2. Right? We have to find two indices I and j such that the absolute value of I minus j is greater than or equal to x. All that really is stating is that the values I can compare the current value to have to be x away. Right? In this example, if this was the example, 4 is not 2 items away. Right? The item that's 2 items away is from the second 4 is here going left. Right? It's at this point going left. These are the elements that this 4 can look at because the elements have to be x equal to 1, 2 elements away, right? So we can look for the closest y for this x, but it has to be at least 2 elements away. So that's kind of what makes this problem a little bit more complicated than something you might be familiar with. And to solve this, well, of course, the linear time algorithm or n squared algorithm would be for every element, look at all the elements that are greater than 2 away, right? So you look at this element, if you had x, y, z, a, b, c, d, e, f, whatever, right? What you do, the brute force approach would be for every element, look at all the elements that are x elements away, right? So for B, if x was 2, you would look at x, y, z, right? And then if you looked at C, you would look at x, y, z, and A. Right, for D, you would look at X, Y, Z, A, and B. Right, so you look at each element and you look at all the things that are greater than or equal to X away from it and find the minimums, and you do that for each thing, right? But that's going to grow with n squared time. And in this problem, we are dealing with nums linked 10 to the 5, so n squared would be 10 to the 5 times 10 to the 5 is 10 to the 10. It's far too slow, right? Okay, so that's not going to work. So I guess the first thing we can do in this problem is simplify it a little bit to think about how you would solve this in another scenario, and then how that can be built on to get to the constraints of this problem, okay? Now, when you're trying to find the closest x to y, well, then you're just trying to find the y's that belong with x. What I'm saying is, if you had a couple people, okay, let's say, for example, you had a few people of different heights, okay, and they were given to you in this order. Okay. So say you had 4 people, right? And let's say that the closest people in heights are, you know, this guy and this guy, right? Now, you could compare all their heights one by one, right? I could compare this first guy to this guy, to this guy, to this guy, right? I could compare this guy to this guy, to this guy, this guy, to this guy. I could compare all of them to each other, right, in n squared time. Or since the person that's closest to me in height, right, is the person that belongs next to me sorted. So what I mean is, if you took this system, you wouldn't have to compare everybody to everybody. But if instead you took it and you sorted people in terms of their height, like this, right? Well, then you would see after you sort it, well, whoever is going to make the minimum difference is somebody next to me, right? Because the people next to me are as close as possible to my height. That's why they were put next to me, right? If I'm in a sorted list of people, a sorted list of people in terms of height, the people that are closest to my height is the person that's barely shorter than me and the person who's barely taller than me, right? So if I have this list, I can find out who would be closest to me by just looking at the person when sorted is to my left and to my right, right? So instead of having to compare this person to this person, this person, this person, this person, this person, if I sort the list first, if I sort the people in terms of their heights first, all someone has to do is ask their neighbor, right? This person only has to ask their neighbor. This person only has to ask their 2 neighbors. Sorry, there's a delay. Right, this person, neighbors. All you have to do is ask your neighbor, right? This person only needs to ask these 2 people, right? Because the person shorter than me and the person shorter than that person, right? If I'm person A, this is person B, this is person C. Person C is never going to be closer to me because person C is shorter than somebody that's already shorter than me, right? And person B is taller than person C. So I'm hoping that this idea makes sense, right? If you want to find, you know, the minimum difference, well, then just sort the system first, right? Because if you sort the system first, then only the people adjacent to you are potential candidates, right? Because everyone else is either taller than them or shorter than them. Those are the 2 people that are as close to you in height as possible. And you might ask, well, why do it sorting? Why do it? Well, because sorting we can do in n log n time, right? We can do this in n log n time. We can take this system, and in n log n time, we can convert it to this system. Versus trying to compare everybody brute force is n squared, right? So we just shaved off that n, replaced it with an log n, and we're going to get much better performance this way, right? So instead of comparing me to everybody, let's only compare me to the people that are as close as possible to my height, because what I'm really trying to do again, right, is I'm just trying to minimize the absolute difference. I'm trying to minimize the absolute difference between what? Trying to minimize the absolute difference between 2 closest x and y. So I'm trying to find the closest x and y. So who's closest to me in my height? When sorted, the person to my left, the person to my right. I'm not going to keep iterating over this point. I'm just hoping that that makes sense, right? So in this problem, right, this idea makes sense, but the extra constraint kind of messes it up, right? And there is, I guess, I take it back about the example not being good, because this is the same thing as x being 1, right? When x is 1, I can look at any element to my left or to my right. It does not matter. Okay, so let me write down this example, and maybe we'll use this as a reference, and then show when we expand x how that changes the solution, right? So, for example, if we had 5, 3, 2, 10, 15, okay? So 5, 3, 2, 10, 15. There's going to be a considerable delay, and I apologize. I'm going to get a new computer soon enough here. So 5, 3, 2, 10, 15. All right. Now, again, the brute force approach, if x is 1, then that means I can choose any element, right? Because I can choose an element that's right next to me, right? So what we'll do first is imagine that these are people's heights. So we can sort it in terms of heights, right? So we sort the system, right? Boom, we sort the system like this. That takes log n time, and then I can just n log n time, sorry, and I can just check adjacent elements, right? I compare 2 to 3, the difference is 1. I compare 3 to 5, the difference is 2. I compare 5 to 10, the difference is 5. 10 to 15, with 5, the minimum difference is 1. All right, and the reason why I can do that is because, right, and of course this is a result of, you know, these operations, comparing these two things to each other, right? And the reason why I can be sure of that is, well, the closest person to 2 is 3. Makes sense, right? So anybody who comes after 3 will only be farther away from 2. So the minimum difference you can get is 1 in this example. So if I just take a comparison of all the adjacent elements and take the minimum, that'll give me the minimum answer because x equals 1, right? But when this becomes difficult, well, you know, since this is 1, right, things get moved around. Okay? That's what gets weird about this. Because it's 1 away, I don't need to consider where things were initially. Right? But if it's greater than 1, the position of things is going to affect what I'm supposed to do, right? Because let's say the difference here was x equals 2, for example. Just for the sake of the argument, let's say x equals 2. Well, 2 can't be compared to 3 now, right? Because they're right next to each other. 2 can only look at things that are greater than or equal than 2 a distance away, right? So now 2 can't choose 3. So if I sort the system and then say things are adjacent, well, that's not going to allow me to realize that things have to be a certain distance away from one another, right? So that's where this problem gets a little weird, right? So we know for sure, right, that if we take a system where we're looking for like neighbors or things that are close to us, we should probably sort. But also we can't just do that because an element might be right next to me, and when I sort it, it'll be next to me, but it's not actually close enough to me to be the answer. I mean, it's not far enough away from me to be the answer because there's this constraint where it has to be 2 away, right? But what is definitely true, right, is, well, is that can I still use this sorting idea when things are far away? So let's just say generally, you know, we have say we have C1, C2, C3, C4, C5, C6, C7, C10, I don't know, C11, and X, okay? Now, for this example, let's say x equals 2. Or let's say x equals 3, right? Well, not x equals 3. Let's call this Ci for C important. I don't know. If x equals 3, then x can't... If Ci equals 3, sorry. If Ci equals 3, we can't compare Ci to these elements, right? Because it has to be 3 away. So we can only compare it to these elements over here, right? We can only compare it to these elements over here. Meaning that, you know, Ci, the things that can be compared to have to be at least 3 away. So it can't be 1 away, 2 away. It has to be one of these elements. So brute forcingly, I can compare it to each element already. But what if this system was already sorted? Okay. if this system was already sorted, then in log n time, instead of just comparing myself to the person to my left, I could say my member is somewhere in here, and if I just find that closest person, will be gravy, right? If I can just find whoever I'm supposed to connect to in here in an already sorted system, the closest element to me, then we're good, right? So then when I get to CK, another C, all I have to do, so if I add a CK, is add an additional element to this sorted system and then ask again. And that, instead of taking, if it's already sorted, we can do a log n operation doing binary search, right? So binary search allows you to take a system that's already sorted and in logarithmic time find an element that you're looking for, right? Or find the closest element that you're looking for. So right now we're trying to find the closest neighbor to us, all right? And we can write an algorithm that using binary search, right? Says, let's just say, for example, okay, x equals 2, and then we had our sorted array, which was 1, 5, 7, 8, 9. Okay, and then we had two elements, x equals 2, so, and then we're looking for 6. Well, if we binary search 6 in this system, if we binary search for 6 in this system, right, whatever this element is, I don't know what this element is. We binary search for 6 in the system. If we binary search in logarithmic time, it'll find that 6 is supposed to go here, right? And then when 6 is supposed to go there, 6 can go in between 5 and 7. Okay? So instead, we go through the whole system. We keep a sorted, like, delayed array, which is sorted, and then we add in new elements as we go through, right? And in doing binary search in log n time, we can find where we're supposed to go within the system. And this can be done easily. This process of binary searching to find the closest element can be done using bisect. All right, so we can use bisect left, for example. Okay. So that's kind of the first part of this problem, using bisect, which will allow you to binarily searching through. There's one more part where we need to think about how are we going to maintain this sorted array in constant time, right? So let's just start with that. So what we'll do is an infinity inside of it. This, because of course those will never be answers. I'm just trying to make it so that there's boundaries on both sides. So like if you're on the edge of a system or something, you know, you don't go outside of the boundaries of the array. I'm just making it right now where you can never go outside of the boundaries, because any number you have is going to be less than infinity and greater than negative infinity. So it's always within the array. Because like, what if you add something, but it's the last element, what you bisect, meaning like, what if the new element you add is larger than everything in the array? So then maybe the index associated with it is a new index that doesn't exist. So this always forces everything into the array. So this is just a little trick to do that. Okay. And then what we need to do is, well, we'll look at each element. Now we don't need to start with the first element, right? Because we want to start delayed, right? Because if x is 3, well then C2 can't be compared to anything behind it. C3 can't be compared to anything behind it. You have to start at C4. So you have to start at 0, 1, 2, 3. You have to start at the third index. So we'll say for I in range X, and then we'll look at all the numbers. First thing we're going to do is we're going to add the new element to the sorted array, right? So somehow we have to, I'm going to just put insert for now because we don't know what the actual algorithm is going to be, because you're going to see in a second that this doesn't exactly work because there's a constraint. All right. So we're going to do I minus X because we always add the X oldest one, right? So kind of basically when we start this problem, right, we're going to start here. And the first element you can look at is C1. Right. So I'm going to insert C1 into the system. And then I'm going to look at C5, and I'm going to enter C2 into the system. So now the system is C1 and C2. C1 and C2. Come on. Oh, and every time I go, right? Because subsequent calls can call everything that was there previously. All right. Okay. And then we're going to do a bisect to find the closest element. So the closest... don't know what to call it. We'll just call it C, whatever. So we'll do bisect dot bisect. And what element are we looking for? We're looking for the current element in the array, right? We look for C4 in here. We look for C5 in here to find out where it belongs. Okay. And then we say res is the minimum of whatever, because maybe previously we found elements that are closer. And whatever SA is at C. The absolute value of that minus nums of I will be the closest element that's larger than it or smaller than it. I don't know. We'll do it both ways if it doesn't work. And at the end, we just return the min of, not the min, we just return res. That's all you got to do. Okay. Now I'm wondering if this should be bisect left, because bisect, you know, if you bisect, you're going to find your spot, but it might be before or after. Okay. So before we continue, I guess the problem here is when you insert a new element, you need to insert it sorted, right? So it needs to be sorted. This needs to be sorted so you can do a binary search on it. And also what? The other problem is well, when you insert something into an array, right? Depending on where you insert it, it could be linear time, right? If you insert, like if you have a straight array, not a linked list representation, when you insert something into the center of the array, which might happen in this case, right? Because we're adding new elements and it's going to change the order of the array, right? If you have 1, 2, 5, and then you insert 4, well, now you're going to have to shift the 5 over and put the 4 in between, so it's 1, 2, 4, 5. So shifting things can take n time. So we need some way to have a sorted system that's also going to take, hopefully, not amortized, but amortized constant time to insert elements so that this is faster. And the way that we do that is via a sorted set, okay? So instead of making S of A just a straight array, we make it a sorted set. That's a set, so because we're only looking for, it could be a sorted list, but a sorted set because we're just looking for element values, right, that within the range that, you know, meets the conditions and minimizes the difference that as close as possible to us as possible. So if we do a sorted set, now we can insert nums of I because it's sorted, and we can make calls and bisect the system in a sorted fashion as well. So we're bisecting from S of A. Let's try that again. I think maybe I just need the import statement because I have no idea what library it's from. Sorted containers, okay. Sorted sets, can I use bisect? Because the sorted set is just a set that has